Okay, hello. Today we kind of leave our historical astronomy section and start venturing out into our immediate neighborhood, what we call the solar system. Right, so the solar system can be divided into six regions, really. So you have the sun, where over 99% of the mass of the entire solar system resides. So it really holds everything together. But when you think of a solar system, you think of planets. So we have 8 planets. Closest to the sun, kind of these inner planets are what we call the terrestrial planets. These are the planets with rocky surfaces, right? Mercury, Venus, Earth, and Mars are the solar system's terrestrial planets. And again, sometimes they're called inner planets. But their characteristics are that they're rocky. You could stand on them if you wanted to. So out here, kind of in the outer solar system, or the outer planets, these are what are called Jovian planets or gas giants, or sometimes they split them up into gas giants and ice giants, which I'll explain in a little bit. So these planets are much bigger in extent and they're much more massive than the terrestrial planets. So these outer Jovian planets are Jupiter, Saturn, Uranus, and Neptune. So Uranus and Neptune, and these last two, these are the ones that are sometimes called ice giants because their chemical makeup is enough different from Jupiter and Saturn that they're kind of worth distinguishing. But they are still made up of gases and they don't have a solid surface. So, like Jupiter and Saturn, so they don't have a solid surface. So, we often lump them together. Um, Still call them gas giants a lot of the times. And these are the outer Jovian planets. There is more though than just the planets. So in between these terrestrial planets and the Jovian planets, is this thing called the asteroid belt. So this is a region of like just small rocky pieces orbiting the sun. So one hypothesis of how it formed was that this um was like kind of a wannabe planet. Like a planet wanted to form there, but Jupiter's gravity was simply too powerful, it was too great, and it would never kind of let these pieces of rock form into a planet. Um, so it's kind of maybe like our lost planet of the solar system, I guess, if you will. The asteroid belt, though, is also home to one of the dwarf planets of our solar system called Ceres. There's even more, though, out even beyond the orbit of Neptune are a couple of other regions. So the closest region, okay, here's a planetary region. Uh, the closest region to Neptune here is called the Kuiper Belt. And it's kind of a donut-shaped region that goes around the sun. This is where Pluto lives and the other dwarf planets that we know of. The Kuiper Belt also kind of gets lumped into this bigger region here called the trans-Neptunian space. Um, it's technically different, but they're kind of used interchangeably. So we kind of have this area between Neptune and this place called the Oort cloud, where we have a lot of where Pluto lives, where other dwarf planets live. Um, and it's composed of smaller rocky bits that differ from the asteroid belt, and that these are also pretty icy. The Kuiper Belt starts about 40 times further from the sun than the Earth is. So it's really, really cold. That's why, well, we're able to have so many icy objects out there. A lot of comets with a period of less than 200 years comes from the Kuiper Belt. We call these short period comets, and they are very likely Kuiper Belt objects. But out beyond this region, this Kuiper Belt trans-Neptunian space region, as I mentioned, is something called the Oort cloud. This is actually kind of a theoretical region. We've never, like, with a telescope, seen something currently in the Oort cloud, but we're pretty sure it exists. So it's basically a big sphere of rocky and icy objects, kind of just enveloping the entire solar system. And we know that it's there because of the trajectory of some of the comets that we've seen. So I know I said that a lot of our comets comes from the Kuiper Belt, and that is true. But sometimes we get a comet, and when we calculate what the trajectory of its orbit is, it doesn't make sense for it to come from the Kuiper Belt. It looks like it has to have come much further out. So that's where we get kind of this Oort cloud. It's home to what we call long period comets. So comets with a period of more than 200 years. Kuiper Belt has short period comets, Oort cloud has long period comets. And sometimes these periods can be tens of thousands of years. So in general, we have the sun right here. We have this planetary region that has the planets. Unmarked on here, but kind of exists here, is the asteroid belt. Then we have the Kuiper belt or trans-Neptunian space. This is where Pluto lives. It's where other dwarf planets live. It's where we get short period comets. And then we have way, way, way far out into space. We have the Oort cloud, which is where we get long period comets. So, as we kind of got the sense of these past couple weeks, humans have been studying the planets for a really, really long time. So we must have everything figured out, right? So this is not the case. Like, we do not have everything figured out. There are still huge blank spots in our knowledge of even our solar system, like the closest things to us. So, for example, we still don't have a complete census of exactly what is out there. So all we really know about the Oort cloud is what we know from comets that come close to the sun every once in a while. Um, in the early 2000s, there was a spate of dwarf planet discoveries. So we even don't have a perfect idea of what is out in the Kuiper Belt. Um, the solar system is much, much more than just the planets and the sun. There are all these smaller bits out there that can tell us a lot actually about the next question, which is, how did the solar system form? We kind of have a general idea of how planetary systems form, but the details are fuzzy. And all of these small, icy, rocky bits kind of hurtling around the solar system that are not planets can illuminate that. Related to how the solar system formed is the question of how unique our solar system is. How common is it for stars to have many types of planets? Our solar system's planets seem pretty organized, right? 4 rocky planets close to the sun, 4 gas giants farther away. So how often do other planetary systems organize themselves like this? And how does that happen? Um, are there types of planets we have in common? Or are there other types of planets that populate other star systems? So we need to know and understand our own solar system before we can truly answer these questions with any certainty. And then, as always, a motivating question for studying the solar systems and exoplanets, right? So planets that orbit other stars, is whether there is life elsewhere in the galaxy and whether we can detect it if there is. So how might we go about tackling these questions? So we can start by actually figuring out what is out there other than planets. So we can look at the satellites of planets, so moons. Um, we can ask, how did these form, right? Is it the same for all planets? For example, Earth's moon is a little bit of an oddball. The moon is actually quite large in relation to the Earth. And we don't have really kind of all the details of the moon's formation kind of hammered out, but the hypothesis is that the moon formed early in the solar system's history when the Earth got slammed into by a Mars-sized object. So other moons probably didn't form that way, or they don't necessarily have to form that way. And so the question is, where do moons come from? Um, there are many, many moons in the solar system. There are only three in the inner solar system. So Earth has one, Mars has two, but there are dozens around the Jovian outer planets, right? Jupiter has, I think at last count, 95 moons. Saturn has the most with an official count of 146 moons. Uranus has 28 and Neptune has 16. And a number of these moons actually are really geologically and chemically interesting. So Europa, for example, it's one of Jupiter's moons, one of the Galilean moons. It's the subject of study for a spacecraft called the Europa Clipper, which was launched just last fall. And it was designed to study what is probably a salty subsurface ocean and to look for the chemical building blocks of life. So if you're an astrobiologist, this is a very exciting mission. Titan is Saturn's largest moon. It has a very thick atmosphere of nitrogen and methane, and that makes it very interesting. And Triton, which is Neptune's largest moon, it's interesting from a perspective of how planets get their moons because it actually orbits in the opposite direction from Neptune's other moons, right? It has a retrograde motion. And this is an indication that Triton is actually a captured object. So it came from maybe somewhere else and got bound up in Neptune's gravity. So where did it come from and what is it made of can tell us a lot about the outer solar system. Something else that exists in the solar system are actually planetary rings. Saturn's rings are the most famous, but actually all of the outer gas giants have rings. So right here, this is an image taken with visible light from the Cassini probe, but the rest of these are taken by JWST, which is an infrared telescope, and it really kind of brings out the rings. So Jupiter has very thin rings around here. This is one of its moons. Uranus, it's tilted on its side, and we can see these rings face on here in the infrared. And Neptune in the infrared, you can really see those rings. Okay, so this was just a very brief, fast and dirty overview of the solar system. Next time, we will talk in more detail about the individual planets, their composition, and their geology.